corner from La Laguna. And let me give you a little bit of an overview of his research career. So he graduated in physics with a specialty in astrophysics here at the University of La Laguna. And then he moved to the US to do his PhD at the University of Florida. Then he has had different research positions, for example, at the University of Texas at Austin, also in the USA. Then he moved to Japan, to the National Astronomical Observatory of Japan now. And then he was working for NASA at the Ames Research Center, where he was working for SOFIA, the stratospheric observatory for far infrared astronomy. So he was actually flying with the SOFIA many times, taking far infrared observations. And now he's a senior research scientist at the Kavli Institute for Particle Astrophysics and Cosmology, KIPAC, at Stanford University, also in the US. He moved to the US and he never came back, unfortunately. And in the summer of this year, he will be moving as an associate professor at the University of South Carolina, where he will help to form a new group on extragalactic magnetism. So Enrique, the floor is yours.
Thank you so much for the intro. And it's a pleasure to be here in my hometown. I'm from La Verdillada, which is a kilometer from here. So it's very nice to be home and talking about what I've been doing for the past few decades, or a decade or something like that, I'll say. So magnetic fields, I know nobody have run and walk away. So just relax, have fun, and try to figure out what magnetic field tell us about galaxy evolution, star formation, and what kind of information can we get from the dust properties of galaxies. Okay? So everything that I'm going to show here is being thanks to the amazing team that we have been working for the past several years from the SALSA project, figure out where the SALSA comes from, all those letters. But basically, it's two PIs on my side in the US from the far infrared side, and we have Ann Mao, in the Max Planck, expert on radio parametric observations, but we have people expert on pure theoretical work. We have people from here in the IC, experts on galaxy dynamics, far infrared instrumentation, and also molecular gas and H1. So let's start big, and let's start with the whole universe. So here what I show is, let me stop it for a second. So what I show here is a radius transfer, non-streaming cosmic ray injection magnetodynamic simulation done by Sergio, which is my postdoc in Stanford for the past few years. And here what you're gonna see is like 20 megaparsec scale MHD box with all stellar feedback physics, MHD, cosmic rays, radius transfer with a spatial resolution of 10 parsec scales. So every single dot that you see there is actually a galaxy with a 10 parsec resolution. Okay, and what you see on the background is the gas distribution as a function of the cosmic time. Here in the redshift, you will see it. So typically, what you see is the gravitational collapse and the dark matter interaction, creating the cosmic web, and you see major and minor mergers in the center, creating what you have galactic outflows. You have spirals. Also, you also have a starburst, and ending up with a giant elliptical galaxy in the center with a bunch of satellites around, and you have a few small galaxies on the filamentary structures. Because we have a full MHD simulation, we can have the same picture, but from the magnetic energy point of view. So what I'm gonna show now is the same background, the same image here on the bottom, and on the background, what you're gonna see is the dots are the same. So this is the stellar distribution, and the background is gonna be the amplification of the magnetic field as a function of cosmic time. So you start with a very low magnetized universe, 10 to the minus 12 Gauss, and what you see there is the magnetic field amplification due to gravitational collapse. So the magnetic flux should conserve. So if you collapse the magnetic field, so the area decrease, so the magnetic field flux should increase. The other way that you see, in order to amplify the magnetic field, is due to large scale dynamo, basically differential rotation of the galaxy. And the other way, I don't know if you see it very well, but you see some kind of like bubbles being pushed away. That one here was very cool. Actually, you see some bubbles here. And those bubbles of magnetic field energy are being generated by supernova explosions. What you have here is the injection of turbulent energy into the ISM, in the interstellar medium, and the synchrogalactic medium. This turbulent energy transferred to magnetic energy. This is the dynamo process. And then it amplifies the magnetic field from the 10 to the minus 12 Gauss all the way to 10 to the minus 6 on to 10 to the minus 4 Gauss. So there is a gap, but knowledge gap without any empirical measurement from 10 to the minus 20 to the minus 16 Gauss from the beginning of the universe that's been created for some fluctuations of plasma fluctuations and stabilities at the beginning of the universe to 10 to the minus 6 Gauss in the typical ISM. And there's no single measurement here. We have present day and we have some theoretical estimation. And the model is telling you that you have this dynamo effect, which is the conversion of turbulent kinetic energy into magnetic energy that allows to the amplification of the magnetic field due to gravitational collapse, supernova explosions, AGN, and differential rotation. Yeah, so it's like 1 to 2% of the injection is enough. I have these simulations. I have a follow-up slide about it. Do you have a question? Oh, sorry. So yeah, so these are from simulation. So the question I want to answer today or trying to address are, so how has the magnetic field amplified by the interaction and the star formation in galaxies? So what are the B field properties across the multi-phase ISM? And is the circumgalactic medium magnetized? And how much is magnetized there? Because you see that you end up with a fully magnetized universe nowadays. So what do we know now? So far in the past 40 to 50 years, everything that we know about extragalactic magnetism is through radio parametric observation. So radio parametric observation, you're tracing synchrotron emission of comet ray electrons orbiting around the magnetic field in galaxies. So you're tracing the magnetic field in the warm and diffuse ISM. And here what you see is like in the background is the optical, it's a combination of optical image or radio emission, and the lines are the magnetic field orientation. So the typical spiral galaxies has a highly ordered kiloparsec scale B field, normally following the spiral arms. You have a contribution of this ordered B field plus a turbulent B field. I'm going to be talking a lot about that. The ordered B field is this kiloparsec scale spiral B field, and the turbulent B field is the small scale turbulent magnetic field due to star formation, for example, or tangled B field due to filamentary structures or interaction of galaxies in this case. So if you look the galaxies and edge on, you have this typical X shape that the people have tried to figure out what it is. This is the magnetic field above and below the disk at several kiloparsec scales. People think that this is a topic that been for decades trying to figure it out. People think this is a large scale big field as a spiral big field in the halo. The new observation using Meerkat in the South Africa observation. So this is a beam size of almost a kiloparsec scale. The beam size of Meerkat is around a few hundred parsec. And observing this galaxy, what you see actually there are chimneys of magnetic field going upwards, above and below the disk. Yeah, so what you have is you have the local magnetic field, and then you have the electrons orbiting, spiraling around. So then what you have is you use polarization observations, and what you observe is the orthogonal component of the magnetic field from the electron perpendicular to the orientation of the magnetic field. So what you have is that you observe the radio polarization has a preferential orientation, which is the linear polarization, and then on that side is always perpendicular to the orientation of the magnetic field. This is the orientation. The direction, you use parallel rotation, so rotation measure. And the rotation measure tells you the direction of the magnetic field along the line of sight. So you have positive or negative direction, tell you the direction the way that you need to use. So just a follow-up. So the irregular galaxies, you see they're more a little bit messy, but interestingly, you have this spiral. Some of them show this spiral field, which show that these irregular galaxies have some kind of rotation on it in order to create them. And also you have this radial B field, which are usually along the direction of the galactic outflows. And mergers also have this spiral B field and also B fields along the tidal tails. And usually the stronger B field are measuring these interacting galaxies just because the compression of the B field. So our approach is different and it's new for the past few years. Rather than using synchrotron emission, we're using magnetically aligned screen. We are placing the magnetic field in the final galaxy. Here what I show is a toy model of the polarized TV. So what is the spectral distribution from the polarization point of view. So the synchrotron emission is a power law, or maybe you have some true over at some point, but the power law spectrum. And here what you normally observe in the radio perfume observation, they usually up to 60% polarized from no. So it's up to 60% polarized. So people 40, 50 years ago tried to do optical polarization, but the optical polarization are mainly dominated by electron and scattering. This doesn't tell you anything about magnetic field, so it's just the electromagnetic radiation being scattered as a mirror shape due to the dust in the galaxy or the scattering. So you have something of related data, but about the magnetic field. So what we know is, so what we use is the magnetic line. So here, what happened is follow. This is a little bit tricky. Okay, so this doesn't work. That was on, right? Yeah. Okay. So here, so you know that okay. So this is usually it's a misconception of how the aligns, how the dust grains align. So usually what we have is you have elongated dust grains composed with carbon, nitrogen, oxygen, and some silicates and iron inclusions. And what you have is you have these dust grains in the ISM that's being radiated by starlight, and because they are elongated, this radiation creates a pressure in the elongated dust grains that spins the dust. And so then you have a spinning dust grain with the greatest moment of inertia parallel to the short axis of the dust grain. Because the dust grain are paramagnetic, meaning that you have some iron inclusions on it, it creates an internal magnetic moment. And then now you have two moments of inertia. You have the moments of inertia of the spinning dust grain, and you have the magnetic moment. So both of them doesn't necessarily need to be in the same axis. So now it's a matter of what is the time scale at which the dust grains align with the radiation pressure or with the local magnetic field. And it turns out that the typical magnetic field in the ISM, which is a few microgauss, for a typical ISM dust grain size, it takes 10 to the minus 5 seconds to align at that grain. Where the radiation pressure of typical ISM for radiation by star formation, it takes a few seconds to align. So every single dust grain in the typical ISM in the galaxy are aligned by the magnetic field, which magnetic moment of inertia is along the short axis of the dust grain. So that means that the long axis of the dust grain is perpendicular to the magnetic field orientation. So what we are doing here, like we are measuring the emission of the dust grain in the far infrared. That emission has then, because the dust grains are elongated, then what you have is a preferential orientation of the electromagnetic radiation that is perpendicular, that is parallel to the long axis of the dust grain. And this is what I'm trying to show here. So there is emitting, and more emission in this axis than in this axis. So then the electromagnetic wave is polarized along the long axis of the dust grain. So and this is the linear polarization that we get. So in order to infer the magnetic field orientation, so then you just rotate by 90 degrees and you have the local magnetic field orientation. And you have it that way. So just take into account that our beam size at 300 parsec scales, and these are in average 0.1 micrometers. So we are doing microphysics of the local magnetic field with beam sizes of 300 parsec scales, which I mean, I love this part. So how do we do this? So from the ground, we use a ALMA in the submillimeter, around 800 to 800 microns to 1 millimeter. The GSMT in Hawaii, 850 microns. And for the past few years, as Christina was saying, I did more than 100 flights on this airplane to get the polarization observations from 50 microns to 214 microns. Just basically tracing the peak of star formation radiation, or star formation in the local ISM, in the ISM of galaxies. So this is imaging observations sensitive to the linear polarization. Okay. So what we do is we form this SALSA project with the idea of doing the first comprehensive study of magnetic fields in the multi-phase ISM. So multi-phase because we had the radio polarization, and then now we have the far infrared from the cold and dense ISM, and also try to figure out a way to correlate the magnetic field structure and polarization measurements with the dynamics and galaxy types from 102 kiloparsec scale. So you want all the data I'm going to show here today is in our website. So you have all the observations in far infrared and radio. You have the CO and H1 from things and fans and little things projects. And then we also have the maps per lyosci of the dust temperature and column temperature. We have Python codes in order to analyze all this data, just in case you are interested. So, okay, results for now on. So big fields, magnetic field permeate the cold and dense ISM and also the CGM. So these are all the observations. Every single galaxy that we have is around 16 galaxies. We have a combination of spiral galaxies, radio-long, radio-quiet, AGN, and starburst galaxies, and we have some mergers. In every single one of them, we observe this large scale, kiloparsec scale magnetic field in the cold and dense ISM. So the cold is for the wavelength that we're observing, 20 to 60 Kelvin, and the density is around 10 to the 20 to 10 to the 23 centimeter to the minus 2, so NH. Okay, so this is what I define as cold and dense in this case, which is different depending on the places that you're working. So let's focus on the spiral galaxies. They are the most simple one, and then give us a baseline to understand the most complicated ones. So here in both far infrared and radio, so we observe this spiral order B field that dominates in both the far infrared and radio wavelengths. So here in the background, you have the far infrared emission from Sophia. The black lines are the magnetic field orientation in the far infrared at 154 microns, and the white lines are the radio synchrotron emission observation. This is a work done by Alex. Some of you will know because he was here. And then what we did here is to calculate the pitch angle, which is the angle of the magnetic field orientation for a specific annuli, assuming a centrosymmetric pattern. So then that will give you how much open or closed the magnetic field is single galactocentric radius. And you see that in general, you have some kind of like constant pitch angle across the galactocentric radius in both radio and far infrared. The differences are the most interesting part, so I will go and talk later on. But basically, you have a dominated B field. So here, the point is that we assume a logarithmic spiral B field, and this is a big assumption. So why you should assume some parametric B field structure. So we worked with undergrad with Will for the past few years. So he started as a second year a college student, and what we did is to do a non-parametric analysis of the magnetic field structure. And here what we did was to decompose the magnetic field structure in modes, in the same way that the people do for a CMB to estimate the EV modes. Here what you have is like you estimate you separate the magnetic field in components. Like for example, the M0, the mode 0 is a constant B field. The M2 is some spiral B field, and then you add some weights in both of them, and then do a linear combination of them. So you end up with some spiral B field, but it's a little bit offset, right? So then you can do that with the whole galaxy, and then in radio, far infrared, and you find that the highest relative weight of the modes is M2, and that is telling you that you have a large scale spiral B field dominating the galaxy, but you also have a M0 dominating in both radio and far infrared, which is this constant B field. The interesting part is that is the relative contribution from the radio and far infrared. So in radio, you have this large scale B field, and you have some residual at large at high modes. This is basically like some kind of like disordered B field. But in radio, you have the M0 and M2 have the same weight. So you have still you have M2, but you have a very high contribution of disordered B field in the disk of the galaxy. And this is something that you can see here very, very well. So this is the pitch angle, and you see both of them in radio and far infrared are kind of constant, but then the point is like, what is the angular dispersion of the pitch angle across the galactocentric radius? And this is telling you that you have, in radio, you have almost a constant pitch angle, so spiral B field, but the radio goes all over the place. And here, so you see very clear. So you have this spiral B field in the radio, but then you have, for example, a radial B field in this case. So in this spot of the star formation, you have another one that goes away, and these are the peaks that go all over the place here. So that is telling you that you have a large scale B field that is there inherent because of the differential rotation of the galaxy, but only the far infrared trace a small scale B field due to the injection of energy by the star formation, for example. This is all our star formation spots here that actually change the magnetic field structure from the typical ISM of the galaxy. So the other way to look at this is to do the correlation between the degree of polarization, polarized intensity, and total intensity as a function of the column density, right? And here what you have for each line of sight, so here's the total intensity of the background, the polarized intensity, and the column density, and just plotted over the degree of polarization, for example, right? And then you can see, like, you see that the degree of polarization has some slope, so you are losing polarization as you are increasing the column density, but there is some specific column density for this set of galaxies that we have here, which are most of the galaxies. So it changed the slope radically. And then this means that you're losing a lot of polarization at the higher column density. This polarization is the multiplication of the how much light is polarized and how much total intensity you have, right? So this is polarization is the polarized intensity divided by the total intensity. So if you're losing polarization, that means that you are having an increase of total intensity. And increase of total intensity meaning that you have a isotropic B field or some random B field, some unpolarized intensity, adding light into the same beam. And when you plot this line on top of the column density, you see that these are co-spatial with the region of star formation. Here, and in this case, you have the whole ring is the star formation region. So that means that the far infrared, in this case, you have a sensitive to the amount of star formation in the galaxy. So you can use the degree of polarization in order to estimate how much star formation activity you have in the galaxy. So using this slope, so this is a general for a bunch of galaxies. So, but I did this study for each one of the galaxies, and you have a slope of how much polarization are you losing in the galaxy. So then what you can do is to plot the depolarization rate, basically how much polarization are you losing as a function of the surface star formation rate along the line of sight. and plotted as a function of the global star formation rate of the galaxy, just to try to figure out if you have some information on star formation or not. And you do it with both, for radio in blue and far infrared in red. You see that radio is almost flat. I mean, this is the slope is 0.05 plus minus 0.5. I mean, this 4, this is flat, basically. So that means that the radio polarization observations that have been done for the past 40 years are insensitive to the global star formation rate of the galaxy. So, but if you look at the far infrared, you see a decrease of polarization. You are losing a lot of polarization as the global star formation rate of the galaxy increase. So that what implies is that you have a lot of star formation, you have a lot of injection of energy due to the star formation in the ISM that is disordering the magnetic field in the far infrared, which is sensitive in the far infrared, but it's not in radio at all, at least in the 500 parsec scale regime that you have. So all these far infrared observations that I've been doing, so the point is like all these far infrared observations that you've been doing for the past few years, and you want to get any information about the injection of the global star formation rate of the galaxy, is totally insensitive. You have no idea about what is the global star formation rate of the galaxy just by looking at the synchrotron emission. But if you want to know the relationship between how much star formation is injecting or putting energy into the ISM, you need to use a far infrared observation in this case, because you're tracing the cold and dense ISM, which is co-spatial with the star formation regions of the galaxy. So this is all observations, but we have the simulation of Sergio, so we can do the same exercise in this case. So we can obtain the physics using the MHD simulations here. So in this case, we have the same cosmological box with several realizations. The several realizations and several magnetization in this case. So here what I show is the optic is a mock observations in the optical, in the far infrared, and in radio. And every column is a different realization based on the original seed magnetic field of the simulation. Here MB is magnetic field 10 to the minus 20 Gauss, 10 to the minus 10 Gauss, minus 11, minus 12. So the two simulations that are completely unphysical are these two here. So the 10 to the minus 20 Gauss, this is basically a hydrodynamical universe without any magnetic field. And you see that the galaxy, the final galaxy, is a very filamentary with a lot of star formation going on in the galaxy. Actually, the star formation of this universe is more efficient than the real universe. On the other extreme is a universe that is dominated by magnetic field, 10 to the minus 10 Gauss. So this is a completely physical universe that actually the magnetic field has influence in the dynamics of the galaxy, which is not true. But in this case, what you have is a very compact galaxy with little star formation going on in the galaxy. So basically what you have is the magnetic field is creating is counter balance the gravitational collapse of the star forming regions, and also is compacting all the galaxy to only a few kiloparsec scale. So this is, but you see now that pure HD is not real, and a pure HD, of course, is not real, but you see the magnetic field has influence in the star formation efficiency of the universe. So your question about the ejection, so we have one realization where it's a HD, but the magnetic field is only injected by supernova explosions. And in this case, we have a star formation efficiency that are similar to the universe that they found as a function of the comet rate. And the final magnetic field strength are typical 10 to the minus 6 Gauss without any seed magnetic field at all, which is very interesting in this case. No, no, it's no. The halo mass doesn't depend on the magnetic field. Yeah. And in this case are the two that are with a seed B field of 10 to the minus 12, 10 to the minus 11. They're very similar to the typical galaxy. The only thing is just you have for M to the 11 a little bit stronger B field. you have more diffuse synchrotron emission in the galaxy in comparison with this one. But these two are pretty similar to the typical universe. So when you compare the mock observation with the observation that we have from Sophia, for example, and radio, here on the top you have the mock observation. In blue is the radio emission, and in red is the far infrared. The lines are the magnetic field orientation. Then you see this large scale big field. I'm breaking everything. This is because I'm moving. So this is because you have the large scale big field that you see in radio, and you have the small scale magnetic field in the far infrared too. So this is quite interesting. So here the point that I asked Sergio when he joined is like, okay, we have the radio and we have the far infrared, but we are talking about the emission is coming from the diffuse ISM or from the cold ISM, but I wanted to know specifically, physically, where the far infrared is coming from and where the radio is coming from, and in total intensity and polarized intensity, exactly in the spatially located in the galaxy. So what we did was to isolate galaxies, and then what you can do is like create a slides of the galaxy, and then do a vertical height estimation of how much emission you have as a function of the vertical height. And here you have the radio, far infrared in total intensity, radio, and far infrared in polarized intensity. And the rows, you have a slot of only 200 parsec of the galaxy, and then increase all the way to 2 kiloparsec scale of the galaxy. And you see that in radio, most of the emission is coming from regions above and below the disk of the galaxy. So, and the far infrared, the center 200 parsec is and the 2 kiloparsec is not much difference into the total intensity. So you can do the curve, the growth curve, and then the rule of thumb is like the 80% of the emission in the far infrared is coming from the central 100 parsec, and the 80% of the emission in the far infrared is coming from 200 parsec or above. So all the radio emission is coming from above and below the disk. That's because you have these large scale big fields, and you have the synchrotron emission orbiting around 200 300 parsec scales. And the radio, the far infrared, sorry, you see the polarized intensity is coming from these dots here, which are co-spatial with the star formation rate of the galaxy. So everything that we have observed before is exactly that. So the far infrared is co-spatial, exactly located in the region of star formation, and the radio is located above and below the disk. So you're tracing the synchrotron emission in the CGM, basically, of the galaxy. So with the simulation also, you can separate the core neutron medium and the warm neutron medium, and you can create maps. And this is exactly what you see again. So the warm neutron medium, you have these filamentary structures with a lot of warm neutron medium in the above and below the disk. And the core neutron medium, you see a very thin disk of 100 parsec, very patchy in this case. So this is exactly what we are observing. When you compare with the vertical height of the Sophia observations and the vertical height of the radio observation, you see that the CNM, the core neutron medium, and the infrared emission, the correlation 1:1, and the radio observations with the WCM and a little bit of the CNM is 1:1 correlation. So all these filamentary structures is coming from something above and below the disk, these large scale magnetic arms in the radio. And you don't have information in radio of the magnetic field in the disk at all. You're dominated by something above and below the disk. So in the observations, again, so just come back to the empirical universe. So what you have is the same galaxy with the same angular resolution. In far infrared, you're dominated by the dust emission in the disk, around 100 parsec. And in radio, you have this typical X shape that was shown before, that is coming from some big field above and below the disk from this large scale magnetic field or cosmic ray electrons orbiting very large scale big fields away from the disk of the galaxy. So now you can use both as in order to do a 3D tomography of the magnetic field in galaxies. So it's not only using the far infrared on the radio, so actually both of them give you the whole multi-phase magnetic field in the galaxies. So, and in this case, so just to sum up this part, as an example, you have an M51 here. So you have this spiral B field, but highly ordered. So the ordered B field is just, you have the beam size, which are these circles that I show here. And the large scale B field, that doesn't mean that you have a one line of 3 kiloparsec scale. That doesn't physically make any sense. So what you have is you can have a small loops within every beam due to the star formation or the differential rotation of the galaxy. But the angular dispersion from beam to beam, it has the impression of having this large scale B field. And then when you go to the region of high star formation regions, for example, in this case of M51, you have the angular dispersion of the magnetic field orientations doesn't follow this large scale B field. And this is what we call a fluctuation dynamo or disorder B field. Because in the far infrared, for example, you have a density weighted average polarized intensity measurement that is being weighted by the high density well below the angular resolution of the observations that are co-spatial with the star formation regions. And this is why you have this very high angular dispersion from beam to beam. Because in one beam, you can have a lot of star formation without an injection, tangled debris field or disorder. And then when you go to another 300 parsec, the ISM have completely changed, and maybe you have another star formation rate, a star formation region with another different injection pattern, and then you find this angular dispersion between beam to beam. Okay, so now we know what happened with spiral galaxies. These are the easiest one. Okay. Yeah. So then we can do the same example, right? In this case, you have a very strong star formation happening in the center that's creating these galactic outflows, and it's changing the galactic pattern, the magnetic field pattern in the galaxy. The clear example, again, radio versus far infrared, because we know a lot about radio, and this is the radio observation of M82. You have this magnetic bar, and you have no information of the magnetic field in the galactic outflow, except if you believe this one beam and two beams that looks like something that's going up, but nothing here. And you go to the far infrared, which traces the cold phase of the galactic outflow. You have two galactic components, one parallel to the galactic outflow, all the way to kiloparsec scales, and you have some B field parallel to the disk of the galaxy. So this this magnetic field in the call ISM of the galactic outflow, we have seen it in different galaxies and all the way up to 4 kiloparsec scales. So somehow the galactic outflows is pushing the magnetic field away from the galaxy all the way to 4 to 5 kiloparsec scales away from the disk of the galaxy. So the silly plot that I always do is like how much polarized intensity, what is the extension of the polarized intensity as a function of the global star formation rate of the galaxy. And you see that the different shapes are different wavelengths from 53 microns to 214 microns. And you see that the star formation, this is the global star formation rate of the starburst galaxy. And as you increase the star formation rate of the galaxy, the more extended polarized intensity you have. So the more extended B field you have into the CGN in this case. So something that we can do here, and I'm going to finish with this one, is that you can actually do some physics here and estimate the energy budget of the galactic outflow in M82. In order to estimate the magnetic budget, you need to estimate the magnetic field strength. And something that we use for this is the Davis-Chandrasekhar-Fermi method. The point here is that the Davis-Chandrasekhar-Fermi method was done in 1953 and assumes, it's very simplistic, which assume ISM with only alpha wave, and that is a magnetic wave that's in equipartition with the turbulent kinetic energy. And then you solve the equation, which are very simplistic, and you end up with a relationship that gives you the magnetic field strength as a function of the density of the medium, the turbulent kinetic energy, the dispersion velocity, and this is the angular dispersion of the magnetic field orientation on the plane of the sky. The point here is that this is assumed only one MHD wave and a large scale B field and some turbulence, but we have a problem in M82. So we have a large scale flow on it. So if you want to estimate the magnetic field strength here, you have a stretch, you have a stretching and shearing in the galactic outflow So, and then like you want to estimate it, the shearing, sorry, is stretching the magnetic field. And if you want to estimate the magnetic field strength, you will estimate the magnetic field strength by several orders of magnitude because the angular dispersion will be very small. But that doesn't imply the magnetic field strength is very strong. So one thing that you can do is to go to the ideal MHD equations and then assume two waves in this case. In one wave is the large scale flow, the galactic outflow, and the other one is the alpha wave, so these two waves, and then solve the ideal MHD equation that satisfy this condition, and then you end up with a correction of the typical deficit and second Fermi method that depends on the large scale outflow, and then the angular dispersion of the B field, which is the angular dispersion of the magnetic field on the plane of the sky, and the kinetic energy, which is the dispersion velocity. If you do this, and you can do it per Liouville psi, you end up with the first two magnetic field strength map of a starburst galaxy that go from sub-milligauss to microgauss in the 1 to 2 kiloparsec scale. So once you have the magnetic field strength, you can estimate the magnetic field energy. You have the velocity dispersion, kinetic energy, and then you have the hydrostatic, and you can estimate also the static energy. You can estimate some kind of like a prima beta plasma that the people use a lot, and then you estimate that the galactic outflow is in close equipartition, so the turbulent magnetic energy and the turbulent kinetic energy is in close equipartition up to 1 kiloparsec scale. And you can do it for the three starburst galaxies that you have. I mean, the error bar, I cannot say, so you have the plasma beta go from kinematically dominated to magnetically dominated as a function of the star formation rate of the galaxy. The stronger the star formation rate of the outflow, the more influence the magnetic field you have in the outflow. And the point here is that you have to think about the cosmic rays need to propagate through the magnetic field. This is mandatory. So the stronger the magnetic field, the more complex the magnetic field you have, the more complicated, complex trajectory of the cosmic rays electrons should be in the galactic outflow. More complicated will be to transport the cosmic rays into the CGM in this case. And that's one of the reasons why the radio observations didn't observe any magnetic field in the outflow, because you have a lower, short lifetime of cosmic ray electrons in the outflow due to the strong magnetic field and the complexity of the magnetic field on them. So something that you can do, we have some solar physicists here, so they will laugh about this, but this is like you can use the potential field extrapolation that you guys have been doing for many, many years in order to estimate this magnetic field in the outflows are open or are closed. Open means that close at some point that's very far away from the optical size of the galaxy, or they come back into the galaxy in this case. So I did some collaboration with solar physicists, and we solved the Laplace equation in order to, with two conditions. One is the magnetic field orientation and strength on the base of the outflow that we know, and the other condition is the magnetic field in the infinity is 0. So, and then you solve the equation and you end up with these large scale extrapolated B fields that goes away from the galaxy and doesn't really close into the optical or 10 kiloparsec scales of the galaxy. So you have a lot of magnetic fields going away, at least within the 10 kiloparsec. They don't really close into the optical size of the galaxy. For sure, you have this H1 structure of M82, which is huge between M82 and M81. So these ones will close at some point, but not really in the place that are gravitationally dominated by the differential rotation of the galaxy. But just some for the merger activity in this case. And as I said before, the comet rays electrons the comet rays need to propagate along these lines. They don't gonna go anywhere else. So you have already a restriction of the transportation of the cosmic rays in this case. Okay, and I'm gonna end up with, sorry, I just gonna go. So I'm gonna end up with something that we have been doing that's very new. So this is all the local universe. That's perfect, 1 minute. So we are doing, so as I said before, so we have an empirical gap of the estimation of magnetic field from the beginning of the universe 10 to the minus 20 to the present day to 10 to the minus 6 Gauss. So in order to estimate the magnetic field across cosmic time, we need to figure out a way to estimate the polarized intensity or the polarized from several galaxies along the cosmic time. So what we have done new is to use gravitational lens that start forming galaxies. They are very bright and they're known from the South Pole telescope. And we use ALMA observations to estimate. Basically, we are doing the same at redshift 2.6 that I'm doing with Sophia in the early universe. So in the present day universe, so basically I'm tracing the magnetic field, the magnetically aligned grains in a dusty galaxy at redshift 2.6. And what we observe is 1% polarization with a magnetic field that is co-spatial with the molecular disk of the galaxy. So this is so far is the farthest away magnetic field observed in the universe. So already you have at 3 gigayears after the Big Bang, you already have an ordered B field due to differential rotation of the galaxy. But this galaxy only has rotated twice or 3 times. So you see like how efficient is the rotation of the galaxy to create this large scale B field. And something that's new, that's not been published, we have one galaxy at redshift 5.6. So this is a merger galaxy. And it's polarized at 1% polarization. And we found a 3 kiloparsec scale B field, which is some kind of like in the overlap between the two galaxies. You have the antenna galaxy, it's kind of like antenna galaxy, and you have some dusty region between the two, and you have a B field connecting both galaxies due to the tidal tails in this case. So, and something that you can do is some kind of like a Maddow-Dickinson structure plot where you show the magnetic field strength as a function of redshift or magnetic field strength as a function of star formation rate. For now, we only have upper limits, but the idea is to do a survey with ALMA with like 15 or 20 of these galaxies to do a B field as a function of the cosmic time in order to really give empirical measurement to the theories of magnetic field amplification. And the idea here is like with ALMA, you can use different baselines, and gravitational lens galaxies are beautiful things that the universe has given us. So you can actually use the magnification to reach 50% scales up to redshift 5 with much better than anything that we can do in the local universe. So with 50%, we can resolve the magnetic field turbulence, estimate the magnetic field strength, and correlate it with the kinematics of the galaxy using CO and C1 observation. And you have the full multi-phase ISM and energy budget in the same way that we did with the Starburst galaxy, and do the typical Maddow-Dickinson plots with actual error bars in this case. So for now, they're only expired, but you already see some trend, whatever thing is going on here, but this is something that is happening in the next few years. So with that, so thank you so much, and hope you learned something about it.
Very much, Enrique, for the very nice talk. It was fantastic. Questions, comments? Maybe I'm gonna start. I mean, how large or how is your catalog? I mean, you mentioned the spiral galaxies, but for example, do you have, you mentioned little things as well? So you have measurements of magnetic field, say, on the little things or things catalog?
Yeah, so well, Sophia answered because we finished the whole survey. So
Mhm.
we have 18 galaxies. So they all have things, fun. So H1 and CO, all of them are part of the catalog. So they're spiral galaxies, Starburst, Radio Lava, Radio White, AGN, and Mercury. And we have one dwarf galaxy that has not been published yet.
Dwarf asteroidal.
Yeah,
Wow.
so we have separated. So it would be out.
Okay.
Hello, Enrique. Very nice, impressive, impressive. I just wonder, most of the targets you have been focused are spirals. And then you see, well, the magnetic field tracing the arms. It's all look like in a disc because it's rotating. I see Centaurus say, so my question was, what about spheroids? How, because how is the magnetic field? It looks to me, I do not know well, but I do not see well, but is also kind of rotating.
You have some large scale we feel, but it's highly disturbed because it's post merger, right? It's a remnant of a merger, so it's the angular dispersion of the B field is very high due to the merger. So spheroidal, there's not much dust on spherical galaxies, and also it is dominated by turbulence. So neither in radio you can observe it because you have Faraday depolarization. So no polarization there. And in infrared, no much dust. So we cannot do anything on them at all. That would be pretty cool, but we have nothing to do there. With the metallicity, no directly. So what we can do is to do the polarized energy distribution. So basically, like depending on the dust composition, you should get a change of the polarized intensity as a function of the composition and the intrinsic composition of the dust, and you should see some difference of a slope as a function of the wavelength. And here what I try to show. So you have a decrease of the integrated polarization, and then you have an increase afterwards. I mean, this is something that need to be done with a lot of galaxies. But the point is, like, you can use this polarized intensity with different dust composition and metallicity to prove to try to explain this shape, because the typical ISM cannot explain it, or any model of the ISM, the Astor dust, for example, or Drain and Hensley cannot explain this at all. So maybe you need to have a change of metallicity or change of intrinsic dust composition. But yeah. Yeah.
Thank you. This is more of because I have nothing, no idea of this. I'm curious, like regarding Lottinson, like, do you have any simulations to at least infer like how is the variation of the kind of like follow like star formation density or the ATN or like maybe like shape? This is first curiosity, and the second one is because you're showing very nice resolved ICM. I was wondering, do you have, is it possible to measure the structure like intergalactic medium or like yeah.
Yeah. So if you want something, I mean, if you want the IGM, you can use Meerkat in radio. For example, they have been doing a lot of work, and a lot of data is coming out. So this is like tens of kiloparsec scale B field. You can use it that way, but this you're tracing synchrotron emissions, right? So you're tracing a warm B field in the warm neutral medium. And then for the high redshift, you can use ALMA. I mean, this observation, the 5.6, that's a merger, but it's only 3 kiloparsec separation between both of them. So at least we have some B field between both of them, but that B field is due to the interaction of both of them, not because of AGN or galactic outflow. So the observation that we have, they only have a stellar feedback. It has no AGN at all. So it's something that we need to add in our observations. This is a follow-up that we are aware of it, but in 2 years we need to have another term for Sergio to do that. Yeah, and the first. What? Oh, this part. Yes, yeah. So this is interesting. So like, every simulation gives us different ways. So some of them is like they have a very. So if you use the Illustris or Athena or the other one from Phil Hopkins in Caltech. So you have a very small, you have a slow increase, a slow amplification of magnetic field as a function of mid time. So it normally go peak at around 6 or something like that, and ours peak at redshift 10. So you have a very strong big field, a very high amplification due to supernova explosions and galaxy formation, and then saturates. So the magnetic field energy saturates with the turbulent kinetic energy in the ISM, and you should get some kind of a flat distribution.
Thank you very much. Thank you for the fantastic talk and discussion. And I invite everyone to attend the scientific coffee now in 5 minutes, where you will be able to ask more questions to our speaker.
Thank you. Thank you.
Tenemos preguntas.